In this module of Chapter 8 on Human Demography, Module 8.7, I cover the second of the two life table models on health demography, this one on the multiple decrement life table. This includes concepts, basic model, and a worked example. Multiple decrement life tables are used widely in human actuarial studies to address questions concerning the frequency of occurrence for causes of death and how life expectancy might change if certain causes were eliminated. The conventional single decrement life table shows the probability of survivorship of an individual subject to one undifferentiated hazard of death. In multiple decrement tables, the individual is subject to a number of mutually exclusive hazards, such as disease or, in non-human species, predator and parasites, which means there is more than one way of exiting. Two probabilities, and hence two kinds of tables, are commonly recognized in the study of cause of death. One is the probability of dying of a certain cause in the presence of other causes, the proper multiple decrement life table. The other is an associated single decrement table and is applied to find the probability of dying of a certain cause in the absence of other causes. The assumption of the multiple decrement life table is that multiple causes of death act independently, and it is concerned with the probability that an individual will die of a certain cause in the presence of other causes. The concept itself stems from reliability theory in operations research. The late demographer Nathan Keyfitz used an example of a watch, which can operate only as long as all of its parts are functioning and that each part has its own life table. The probability that an individual, i.e. the watch, will survive to a given age is the product of the independent probabilities that each of its components will survive to that age. The same notation of probabilities applied to internal components causing the death of a system can also be applied to external components such as disease and accidents in humans or predation and parasitism in insects. The concept here is that the probability of an insect surviving to a certain age or stage is the product of all independent risk probabilities. Obviously, the same applies to humans. In general, multiple decrement theory is concerned with basically three questions. First, what is the age or stage distribution of deaths from different causes acting simultaneously in a given population? Second, what is the probability that a newborn individual will die after a given age or stage from a specified cause? And third, how might the mortality pattern or expectation of life change if certain causes were eliminated? The first two questions are concerned with evaluating patterns and rates of mortality, while the last question is concerned with competing risk analysis. In all cases, the analyses are based on three assumptions. First, each death is due to a single cause. Second, every individual in a population has exactly the same probability of dying from any of the causes operating in the population. And third, the probability of dying from any given cause is independent from the probability of dying from any other cause of death. Here we present the data on cause of death by age group for U.S. females from 1999 to 2001, including neoplasms, cardiovascular, accidents, and other. With an initial number of 10 million individuals, the number of deaths between X and X plus N by cause is denoted with this notation, and total number of deaths in this age interval is given by this notation. Note that there was a total of approximately 1.8, 6.2, 0.34, and 1.6 million deaths due to neoplasms, cardiovascular, and heart-related accidents and suicides and other, respectively. The highest number of deaths by age group was cardiovascular in the 85 to 90-year-olds. Accidents were the primary cause of death in young children, 1 to 5-year-olds, and for deaths from mid to late teens, 15 to 20-year-olds. The number of deaths by cause I is given by this formula, where D denotes all deaths. The fraction of all deaths in the interval X to X plus N is thus the sum of deaths over all causes given by this formula. Examples: cohort survival to age 85 is 0.6150. The fraction of all deaths from 80 to 85 due to cardiovascular related causes was 0.1139. Over 17% of all deaths occurred between 80 and 85. Nearly 63% of all deaths in the cohort was due to cardiovascular related causes. over 80% of all deaths were due to cardiovascular and neoplasms. Plotting as a fraction of cause of death by age shows several age patterns. First, other is extremely high in infants due to neonatal and post-neonatal causes. Then from 10 to 40 years, accidents and suicides account for nearly 2/3 of all deaths. At around age 50, there is a major transition when neoplasms and cardiovascular and heart diseases account for around 75% of all deaths. Then at older ages, 7 to 10 deaths are heart-related. The following general formula is used to calculate the probability that a person aged X will eventually, that is, die from cause I between ages Y and Y plus S, is given by the formula given here. The number of life table deaths by cause due to the ith cause of death is estimated by means of the approximation given here. This formula is applied to n dx for the age categories 0 to 1 year and 1 to 5 years, and by 5-year age intervals for ages 0 and over, is given in the table 8.5. For example, the probability of eventually dying of neoplasm-related causes at age 35 is nearly 18%. Competing risk estimation is based on the total probability law of statistics for the geometric mean. Let G denote the proportion of deaths due to cause A. Its complement, 1 minus G, then gives the proportion of deaths due to cause V, or other causes. If P denotes survival probability of surviving both causes as competing risks, it then follows that LNP equal G LNP plus the product of 1 minus G and LNP. Taking exponents to both sides yields this formula. The independent risks are then computed from these formulae. For example, if P equals 0.75 and G equals 0.8, then the independent risk for cause A is 0.7944 and for cause B is 0.7899. For ages from 1 to 45 years, accidents and suicides were the predominant causes of death, with between 4 in 10 to over 8 in 10 occurring in this group. That is table 8.6. Around 70 to 80% of all deaths between ages 45 and 65 were due to neoplasms and cardiovascular combined, in roughly equal proportions. For the oldest ages, 65 through 100 years, cardiovascular and heart-related deaths account for most deaths, starting at around 50% at age 65 and increasing to 80% by 100 years of age. The period survival rates with cause I eliminated are shown in this table, table 8.7, which in turn are used to compute the cause eliminated counterpart survival in this table, table 8.8. The values in this table are then used to compute life expectancy as shown in this table, table 8.9. Note the following. Expectation of life in the presence of all causes is 81.6 years. In other words, none of the causes eliminated. However, eliminating neoplasms increases life expectancy by 2.7 years from 81.6 to 84.3 years. However, eliminating cardiovascular and heart-related diseases had a much greater impact by increasing life expectancy by 7 years, from 81.6 to 88.7 years. This differential in impact is due to the earlier timing of many cardiovascular-related diseases than occur in neoplasms. This ends the second module on health demography concerned with multiple decrement life tables.